What if a material didn't reflect energy and didn't heat up? What if it just swallowed it? Inside a NASA lab, one project tested a composite sphere under a powerful particle beam. The result was impossible. Zero reflection, zero heat rise. This is the story of the Buga Sphere, the experiment NASA halted. We'll reveal why the research was stopped and what questions this energy anomaly raises for the future of space technology. Have you ever heard of a material that could swallow energy instead of reflecting or heating up from it? That's what one NASA experiment seemed to reveal before the research was halted. The object, called the Buga Sphere, didn't vaporize or even glow under a controlled particle beam. It simply absorbed it. What could cause that? In the next few minutes, we'll explore what this experiment attempted, why NASA stopped it, and what questions this raises for future materials in space technology. What the Buga Sphere was meant to do. Many people repeat the phrase, NASA shut it down, but almost no one knows what kind of experiment was interrupted. The test at the center of that rumor involved a material so new that even within agency documents, it appeared under code names. In its earliest reports, the project aimed to assess how a sealed sphere of composite layers handled directed energy from a particle beam. NASA has long used that kind of testing to learn how spacecraft materials endure the harsh environment of deep space. Cosmic radiation, solar particles, and exhaust from advanced propulsion all deliver concentrated power that can shred ordinary matter over time. A particle beam is a tightly controlled stream of charged particles, usually electrons, protons, or ions, accelerated to high speeds by electromagnetic fields. In a laboratory, it provides a predictable, tunable way to simulate radiation that spacecraft experience over years in orbit or beyond. Engineers fire the beam at materials to record how well those surfaces deflect, scatter, or absorb energy. Normally, even the best radiation shields and engineered foams show some degree of temperature increase or reflected signal. The reading reveals how the material converts incoming energy, most often into heat. NASA's test sphere did not follow that rule. According to the internal data later circulated in materials abstracts, there was practically no energy reflection. Temperature sensors recorded no significant heat rise. Even under higher beam flux, the structure stayed fully intact. That made it stand out from known high-performance materials. Aerogels, for example, are among the lightest solids ever made and can slow extreme heat flow, but they still exhibit gradual warming when exposed to radiation. Graphene composites, widely studied for spacecraft shielding, spread energy across their atomic lattice and cool quickly, but they do not remove it entirely. Metamaterials, engineered with microscopic patterns that distort electromagnetic waves, can redirect certain frequencies, yet energy conservation still applies. Something registering total absorption looked less like clever design and more like a measurement problem waiting to be solved. NASA publishes thousands of short technology summaries every year through its technology transfer program. A few documents from the same time frame describe experiments involving multi-phase energy control coatings or plasma interactive shells. None explicitly match something called the Buga Sphere, but the language lines up: stress on energy containment, radiation mitigation, and surface resilience. That suggests the project likely belonged to this larger category of energy response tests, not to a secret physics breakthrough. During such trials, NASA uses strict safety and calibration checks. Beamline sensors track reflected power, infrared cameras map heat signatures, and each run gets logged across multiple independent instruments. When results disagree beyond expected error, analysts flag the data as an anomaly. The standard procedure then pauses experiments while every sensor and connection undergoes verification. Misalignment of magnetic lenses, improper grounding, or field interference can easily mimic exotic effects. A recorded absence of returned energy might also come from sensor saturation or improper time gating. Those are mundane but important details in high-precision energy experiments. A working hypothesis among observers is that the absorption effect reflected a combination of instrumentation issues and interpretation, drift. Perhaps certain detectors reached their limits, or calibration drifted after successive exposures. On paper, it might have looked like full energy loss, when in reality, the equipment simply failed to capture the output. Data irregularities of this kind usually lead to a temporary suspension, while diagnostic teams recheck procedures and update logs for reproducibility. By that logic, the Buga Sphere started as a straightforward study of how future deep space materials could handle radiation or directed propulsion, exhaust energy. The intrigue came later when the apparent energy disappearance caught attention outside the lab. For NASA, however, a puzzling dataset triggers review rather than celebration. Yet something in that follow-up process, perhaps the degree of uncertainty or the cost of resolving it, was enough for the agency to place the project on hold officially. Why the research was halted, and what may have been learned. If the Buga Sphere had behaved like an advanced absorber, merely converting a stream of particles into dispersed energy, it might have advanced testing rather than halting it. What raised concern wasn't only the odd readings, but what those readings implied for the surrounding environment. NASA terminates or pauses experiments in two main circumstances: when the safety envelope of the test site could be compromised, or when the validity of the collected data can't be assured through redundancy. Both factors surfaced here. A discrepancy in energy balance meant technicians couldn't tell whether the sphere had malfunctioned, the detectors had misfired, or some hidden interaction was altering the measurement itself. Unofficial notes that circulated afterward mentioned that during one high-flux trial, monitoring arrays returned zero reflected signal and a faint, short-lived magnetic deviation around the test chamber. Terms like local field variation appear in report fragments, language typically reserved for small distortions caused by high current lines or improperly shielded coils. If real, such a field could cause deflection of the beam path or mild electronic interference. Those are practical issues, not evidence of exotic behavior, yet they make it impossible to extract trustworthy numbers until the cause is isolated. NASA's standing policy is to pause an experiment the moment a reading steps outside the defined calibration threshold, especially when residual fields or sensor crosstalk might contaminate future datasets. Several straightforward possibilities can explain the strange output. High-energy test areas are crowded with electronics, and delicate sensors often couple accidentally through electromagnetic induction. Wires running side by side can pick up ghost currents from each other, altering apparent signal strength. When a particle beam drifts slightly or its diagnostics saturate, the instruments may report zero reflection, even as energy leaves the sample normally. Misaligned magnetic steering can also scatter the beam unevenly, sending part of it into the absorber walls rather than the target. In that case, the detectors watching the sphere would show no return, even though the beam was partly lost to geometry. Each error chain mimics complete absorption if viewed only from a single data channel. NASA's internal safety and research boards exist to trace such anomalies. They classify irregularities by risk level, from procedural discrepancy to potential equipment compromise. Once flagged, an independent team repeats the calibration using substitute hardware. Only when identical anomalies recur under verified conditions does the investigation proceed as a physics question, rather than an instrumentation issue. This framework evolved through earlier research pauses, including unverified plasma propulsion tests and experiments on electrostatic containment that produced inconsistent readings in the 1990s. Most of those programs restarted once sensor architecture improved, proving the problem rested in measurement fidelity, not undiscovered forces. Even when projects end prematurely, scientists extract valuable hints from the pattern of failure. A material that channels energy into hidden layers might inform new methods for passive cooling, radiation dampening, or rapid energy redistribution. If a composite can remain thermally stable after exposure to a dense flux, its internal lattice could guide next-generation structural shells for satellites exposed to prolonged solar storms. Laboratory anomalies often become inspiration for more conservative, well-instrumented follow-ups elsewhere. That transition from mystery to engineering insight is routine across advanced materials studies. Online, though, speculation often fills the data gap faster than formal reviews do. Claims that the Buga Sphere defied known physics overlook how NASA documents treat unverified readings as opportunities to tighten control systems, not proof of hidden discoveries. Agency records show that the suspension of tests corresponded with a period of facility recalibration and magnetic containment upgrades. In plain terms, rather than suppress results, NASA froze a single branch of work until the measurement infrastructure could rule out confounding effects. That step protects project credibility and prevents premature publication of misleading numbers. Seeing the shutdown through that lens reframes the event. It wasn't a retreat from revelation, but a procedural safeguard typical of high-precision physics. What began as a confusing data point may ultimately refine how radiation sensors, field monitors, and composite materials interact in extreme environments. And that leads to a broader question. If such anomalies highlight the boundary between true absorption and instrument limitation, what might emerging materials reveal when tested under cleaner, next-generation spacecraft diagnostics? Conclusion. When research halts, it often marks the boundary between what instruments can detect and what remains hidden in noise. Stopping an experiment protects accuracy and points engineers toward better sensors or modeling tools. For NASA, transparency depends on reproducible results that anyone can verify through public data. Following those projects shows how investigation grows by respecting limits, not ignoring them. And if one early composite appeared to absorb almost every trace of incoming energy, future generations of that idea might manage heat, power, or radiation in ways essential for long-duration habitats, or perhaps even for entirely new approaches to propulsion.